So team one, your job was to, on the front side of this page, talk about conjecture 3. Here the conjecture is that there exists a subset of the plane and a point out of that subset such that no point in S attains the minimum distance to B. So this was the existence question, that before we said, oh, we can always find the closest point on any given set to a point that's out of that set. But this conjecture kind of, I don't know, it's an opportunity to think about that statement a little bit more. So what did you say? Is this conjecture true, that there is always a closest point? Or, sorry, is this conjecture false, that there is always the closest point? Or is the conjecture true, that there exists some example where there is no closest point?
So we said it was true because the point that we pretty much made, where it might not exist if you take it out of the set.
Okay,
If
so...
you want to elaborate on that.
Yeah, so if you let S be, say, the set of points, but you exclude from it the actual point that would have been closest to B.
So this is a little underhanded, but it's totally... Let's actually make this super concrete. Let's suppose that we start with the x-axis as our set, and we just delete a single point. Say we delete the origin.
Right.
So I'm just going to take the origin out of my set, and I have, here is my set S. It's the x-axis minus the point at the origin. And then we pick a point off of that set, let's say 0, 2, or something like that. So here's my point B. So this is a set of x, y, such that y is equal to 0 and x is not equal to 0. So we take the x-axis, we delete one point from it, and then we're trying to find the closest point on the set S to the point 0, 2. And you're telling me what?
So by excluding that point, we now have a union of two open intervals.
Okay. So another way to write this set is it's the union of the open interval minus infinity to 0 with the open interval from 0 to infinity. Right? In other words, pictorially, by eliminating that point, we've created this kind of little, these little frontiers over these little horizon points. So why is there no closest point in this set to B?
Because whatever A1 I might pick on the x-axis there, I can always find, say, an A2 that's closer.
Ah. Right. So this is a sneaky little example where we have a set. It's not now a complete line like the other examples we're looking at, but it's a set in the xy plane which has no single closest point to the point 0, 2. Because whichever point we think is the closest, because these intervals are open as we go towards 0, we can always get just a little bit closer to that deleted 0, and therefore get just a little bit closer to B. So no matter how hard we try, we're never going to get to a closest point inside of this set. So group 3, about conjecture number 5. The conjecture is that there is some way for us to fill in this blank. There's some property that we can say, if S, the set, has that property, then we do get existence. So, did you have a chance to discuss what you would put there to fill in this blank?
We were thinking non-empty subset.
Non-empty. Well, okay, except that the example that Team 1 just came up with is non-empty, but yet does not have a closest point. So, I think we need to be a little stronger. Okay. Any ideas about what it was that made this example fail?
It wasn't continuous.
Well, continuity is a property of functions and not of sets, but you're on the right track.
Should it be closed?
Closed. So this set here, S, is an example of a set which is not closed. Why is it not closed?
They already exist in the real numbers.
Right, it's a union. Well, it's a union of two open sets is one way to think about it. Another way to think about it is that there is a limit point, this point at 0, which is not included in the set. So right, this set S was not closed. And maybe it's that closedness that if we were to close it up by re-including 0, we would get existence back. So maybe closed is enough. I suspect that it is. And what closed, again, means as a subset of the real numbers is something you fuss with in Math 401 quite a bit. But I think it turns out that we can fill in the word closed here and actually get a theorem that works, that we will get existence and we will get uniqueness if we have a non-empty closed subset. I should probably put both of those things here. Then our projection problem makes sense.